Welcome back. In this section of the course, we're going to learn how to work with NumPy arrays. We're going to focus on the different types of slicing and discuss how and when we use the squeeze function. In this particular lecture, we'll explain what basic slicing is and quickly go through a few examples. Right. Since we're starting a whole new topic, let's load up Jupyter and import the NumPy package. After that, we can define the variable we'll be using for this video. In this case, it's a two-dimensional array. So we'll just call it matrix A and assign the values from 1 to 6 to it, split into 2 rows. Good practice dictates that we also display it on the screen to make sure we've defined it correctly. Perfect. Now that we have our variable set up, we can move on to what we'll call basic slicing. Generally, slicing is the act of creating a new array by taking chunks of values out of an existing one. The newly created variable is called a slice, and it can contain entire rows and columns of the original array, or just parts of them. In basic slicing, the slices consist of adjacent pieces of data, like 2 columns side by side, or several consecutive rows. All right. This is best understood through practice rather than theory. So let's get coding. On a new line, write the name of the matrix we defined a few minutes ago, and then add bracket, colon, bracket after it. This is what basic slicing is about. And now we'll explain what it means. As you already know, the brackets indicate indexing, so the only new notation here is the colon. It expresses an interval of values, starting from the row before the colon and ending right before the row after the colon. The default is to include all rows, so if we don't specify anything, we take the entire ND array. Hence, after we run the cell, we see the exact same matrix like the one we defined on the previous line. Okay, so what if we input some values here? Let's add zeros on both sides of the colon and run the cell. We get an empty array. That is because we're telling Python to take the slice of matrix A, starting from the row with index 0 and ending before that same row. Since there are no rows between the first one and itself, this array contains no data. Interestingly enough, its shape is 0 by 3, even though it holds no values. This means that in Python's eyes, this is a 0D array. This is actually very important, and later in this section, we'll discuss why. We saw what happens if we plug in an empty array. So now we can change the second 0 to a 1 and rerun the cell. Well, we get the first row of the matrix. That's because this slice starts on the row with index 0, which is the first one, and stops before the row with index 1, which is the second one. In simpler terms, it includes everything in the interval between the first 2 rows. However, indexing in NumPy is closed open. That means we don't include the upper limit, and therefore, we only get the first row. Thus, if we change the upper limit to 2, we'll get the first 2 rows of the matrix. This is because the slice starts from the first row and goes all the way to the third row without including the latter. Great! It's important to note that slicing can be done for each dimension of an array. So let's call matrix A again and only write colon, comma, colon in the square brackets. The comma separates the 2 dimensions, rows versus columns, while the second colon indicates we're also going through all of the columns of matrix A. If we run this cell again, we'll see the same output as when we only defined 1 dimension. Therefore, we can omit to specify a slice for the second dimension if we're using all the columns. Before we move on, it's important to realize that slices are just smaller arrays. That said, if we call the type function, we'll see that the slice matrix is also an ND array. Superb! If we plan on using the entire array, we probably won't resort to slicing. So let's see how the outputs change when we define some values. On a new line, we can write the name of the variable, and within the square brackets, add a 1 after the colon. Then, if we run the cell, we'll see the first row of the dataset. That's because this notation tells Python to take all rows, starting from the first one, ending before the row with the indicated index, 1. Of course, we already know that this index corresponds to the second row, so the output should just contain the first row of matrix A. Cool! If we move the 1 to the left of the colon, then our slice would start from the row with index 1. As we already determined, this is the second row, so we're taking it and all rows which follow it. Since matrix A only has 2 rows, the output will just be the second row. Fantastic! Let's see what happens when we increase the index to 2. We get an empty array. That's because we're telling Python to take all the rows from the third one onwards. Since there are only 2 rows, it returns an empty array. What's noteworthy is that, just like earlier, even though the sliced array contains no value, its shape is 0 by 3. Therefore, this is another zero-dimension output. This might not seem very interesting right now, but we'll expand on its importance when we introduce the squeeze method later in this section. If we move the 2 over to the other side of the colon, we get a completely different outcome, namely the entire dataset. That's because we're slicing all the rows prior to the one with index 2, which happens to be the third one. Consequently, the last row that will be included in our output is the second row, right? Lovely! Considering what we've seen so far in this lecture, we can say that for any positive number lower than the size of the dimension, n colon and colon n, result in complementary slices, which add up to the complete array. To prove this is the case, let's quickly execute matrix A, 2, colon in brackets again, to see if this is actually the case. We do obtain the empty matrix again, while the first output corresponds to the entire matrix. Great! If you're new to NumPy, all these squared brackets and colons might seem very similar, since indexing is very similar to slicing. In fact, we even specified that we'd refer to one as specific indexing while calling the other interval indexing. Since these can be very similar, let's quickly have a look at several notations that give us very similar outcomes. For starters, if we call the first element of the matrix, we'll see that it's the first row. Now, if we change this to the slice that starts from the origin and ends before the row with index 1, we get the exact same output. The only difference being that the indexing one had only 1 pair of square brackets, while the slicing one has 2. This means that the former produced a 1D slice, while the latter a 2D one. Similarly, if we flip the 1 over to the other side and rerun the cell, we're getting only the second row of the matrix, since the variable only has 2 rows. Then, if we remove the colon and run the cell, we see the same trend. The numerical values are identical, but the outputs vary in dimensions. Superb! As you know, negative values can be used for indexing as well. In a new cell, we can call the slice of matrix A, starting from the beginning and ending prior to the last element. We just use -1 to indicate this and run the cell. The output, as you probably guessed, comprises all the rows up to, but not including, the last one. This is pretty trivial, so let's quickly discuss slicing columns before moving on. If we want to apply slicing to columns or any subsequent dimension, we need to indicate what part of the rows we want to use at the same time. Hence, a column slice would look like this: matrix A, bracket, colon, comma, 1, colon, bracket. The comma separates the different dimensions, so the notation to its left is about rows, or the first dimension, and the notation to its right is about columns, or the second dimension. Hence, it's easy to see we're taking a slice which includes all the rows and the columns starting from the 1 with index 1. The resulting output should contain the second and third columns of the original matrix. To be absolutely sure this is the case, we can quickly output matrix A for comparison. Perfect. So, we examined how to slice rows and columns, but let's quickly see how to slice both simultaneously. Just copy the slicing we just did in a new cell and add a 1 prior to the first colon. This will result in taking the values from the second row onwards, which also fall in the second column onwards. Simply put, we're taking the second and third values of the second row in our example. The output is an array containing 5 and 6, so everything works as intended. Fantastic! Now that you've grasped the fundamentals of slicing, we're ready to increase the complexity. In the next lecture, we'll discuss what stepwise slicing is and how to use it best. Thanks for watching.